Module 3.7, Standing Waves and Strings, Fundamental Frequency, and Harmonics. As we mentioned previously, a node is a point of no movement. If we have a violin, guitar, piano, or other string instrument, the ends of the string are fixed, and therefore they are nodal points. Because of the geometry in a string, if the endpoints are nodes, we have some constraints upon the possible wavelengths of a standing wave in that string. The first possibility would be to have half a wavelength. This would be the longest possible wavelength, since no longer wavelength could have nodes at the ends of the string. Let's go to our wave formula. Frequency equals velocity over wavelength. Remember that frequency is inversely proportional to wavelength, and velocity is constant, assuming the tension of the string stays constant. We can see that since the wavelength is the longest possible wavelength for a standing wave in the string, then the frequency would be the lowest possible frequency for a standing wave in that string. That lowest possible frequency which can sustain a standing wave is called the fundamental frequency. The fundamental frequency is the lowest resonant frequency of a system. We will use the symbol F1 to indicate the fundamental frequency. Now, because of geometry, it turns out we can create other standing waves in a string as well. As long as the nodes and antinodes are evenly spaced along the string, and the endpoints are nodes, we can have a standing wave. Let's go back to the formula. The second standing wave has a wavelength that is half of the original wavelength. Since velocity is constant, if the wavelength is half of the original wavelength, then the frequency must be 2 times the fundamental frequency. We call this the second resonant frequency, and we'll also call it F2. Similarly, the next standing wave would have a wavelength 1/3 of the first wavelength, and so the frequency would be 3 times the fundamental frequency. It will be F3, and so on. When we have resonant frequencies that are integer or whole number multiples of the fundamental, we call those frequencies harmonic frequencies, or simply harmonics. On strings, we identify the standing waves by their harmonic number. This corresponds to the number of antinodes. There's a simple formula for determining the frequency of a harmonic. That is, Fn equals n times F1, where n is the harmonic number and F1 is the fundamental frequency. So if the fundamental frequency of the string is 100 Hz, the second harmonic is 200 Hz, the third is 300 Hz, etc. Now it turns out we can relate wavelength to the length of the string. Going back to our fundamental, L will be the length of the string from end node to end node. We can see that lambda is twice the length of the string, since L is only half of the wavelength. So, for F1, we can say that wavelength is 2 times the length, or lambda equals 2L. For F2, lambda equals L, and for F3, lambda equals 2/3 L, and so on. It turns out that this pattern can be represented by another easy formula. Lambda n equals 2L over n, where L is the length, and n is again the harmonic number. So if we know the length of the string and the harmonic number, we can calculate the wavelength. So if our string was 1 meter long, lambda 1 would equal 2L, or 2 meters. Lambda 2 would be 1 meter. Lambda 3 would be 2/3 of a meter, or 0.667 meters, etc. Now it's time to put more pieces of the string puzzle together. You may recall that we can determine the speed of a wave in a string using the formula v equals the square root of t over mu. Sorry, the dreaded square root has returned. And we just determined that for f1, lambda equals 2L. The wave equation says that f1 equals v over lambda. So replacing lambda with 2L, we get f1 equals v over 2L. And replacing v with the square root of t over mu, we get f1 equals 1 over 2L times the square root of t over mu. Now, what if we want to know the frequency for any harmonic? Since fn equals n times f1, we can create the universal standing wave frequency formula, which is fn equals n over 2L times the square root of t over mu. So, as you stare at this formula, I pose the question, what does this mean? The big picture. Frequency is directly proportional to tension. So if a string gets tighter, the frequency will go up. Frequency is directly proportional to the harmonic number. As you go to the next harmonic, the frequency will be higher. Frequency is inversely proportional to length. So if you shorten a string, frequency will go up. Frequency is inversely proportional to linear mass density. If you change to a heavier string, keeping everything else the same, frequency will go down. A few other items of note. Since frequency equals velocity over wavelength, anything that affects velocity will directly affect frequency. Mu is essentially the mass of 1 meter of string. If you increase a string's diameter, you increase its mass, and therefore its mass density. So, going to a thicker string would lower the frequency of a string. This is what allows a piano to fit into a room. A piano has 88 notes, and the relationship from the lowest to the highest note is over 128 times the frequency of the lowest note. Since f is inversely proportional to the length, if we use the same diameter wire for all piano strings, the lowest string would be more than 128 times the length of the highest string. The high piano string is about 6 inches long, so a low string would be more than 64 feet long. By making the low strings thicker, by coiling a wire around a wire, we increase the linear mass density, allowing the string to be much shorter. To review, the fundamental frequency is the lowest resonant frequency of a system. Harmonic frequencies, or harmonics, are integer multiples of the fundamental. For standing waves in a string, the number of nodes equals the harmonic number. Fn equals n times f1. For a string, lambda n equals 2L over n. And Fn equals n over 2L times the square root of t over mu.